So, hi everybody. Just want to continue on some other topics that are involved in series circuits. The next topic I want to look at is series voltage sources. So, we know that a voltage source provides a constant voltage to a circuit, right? It is also an energy source. So it produces energy for the circuit. And batteries and power supplies are two examples of voltage sources, all right? But we also know, or you will know, that we can also put multiple voltage sources in series. This is often done in particular for batteries. We've seen in our labs that when you use one battery, it's 1.5 volts. 1.5 volts is a very limited amount of energy for many circuits. Many circuits need at least 3.3 or sometimes 5, sometimes 9, whatever it is. So if you have any electronics that need batteries, you know that typically you at least have 2 of them in there. So often the circuit in that electronic device needs at least 3 volts, all right? So we know then that the only way to get that is if we put these 2 or 3 or 4 batteries, one after the other, so that they add up. So as we said there, we can put multiple voltage sources in series so that their voltages add up and give us a larger total voltage. So that kind of looks like this. If we have starting point here, we put a battery there, we put another battery there, and another one here, okay? And we say that they're all 1.5 volt batteries. We then know that the total from, sorry, it's not a minus sign, a plus sign, this is a minus sign. So from this point to this point, we have 4.5 volts. And we did that by adding this one plus that one plus that one. All right. So in a circuit, again, if I do another example, and I have something like this, and really the resistor values don't really matter, but it's just for more argument's sake, just in completeness. So we see that all the batteries are sort of pointing in the same direction, with the minus and the plus, minus and the plus, minus and the plus. And so the current will flow this way. And so we know that an electron that starts here and goes through this battery gains 1.5 volts, then gains another 1.5 volts, and then gains another 1.5 volts to give us a total between this point and that point of 4.5 volts, or total in the circuit of 4.5 volts. All right, so on paper, why would we write it like this? We wouldn't necessarily, but we know that in circuits, the particularly consumer electronics, you need multiple batteries, 2, 3, 4 batteries, typically 1.5 volt batteries that add up together to give us some larger voltage. So it's important to know and understand that, yes, this is how batteries add up. Now, to take that one extra step, right, I'm going to clear this and let's look at another example where we're going to put the batteries in different places, right? But just to kind of prove that it's still the same thing. Because circuits follow all those math associative laws and cumulative laws and distributive laws, you know, where like A plus B plus C equals B plus A plus C equals C plus A plus B, et cetera, et cetera. So it doesn't really matter, you know, which one goes where, as long as we keep our directions right, nothing ever changes to the total circuit, okay? So we'll say this is 1.5 volts, this is 1.5 volts, this is 1.5 volts. Say this is 100 ohms. Make this one 100 as well. Actually, I'm gonna make them all 100 just for fun, all right? And we're gonna put in the current. And so I see that on all our batteries, I've got the plus or minus kind of going in this clockwise direction. So I can guess that the current is most likely going to be going clockwise in this problem, in this question. And that means that the potential drop across this resistor will be like that, across this one like that, across this one this way, and that one that way, all right? And because it's a series circuit, I don't care that there's power supplies in there or batteries. We know it's a series circuit, so I know that our total is just these 4 resistors together. So I'm just going to label them R1, R2, R3, and R4 just for, you know, completeness sake, just to keep things straight. And I'm going to call this VR1. This is VR2, this is VR3, and this is VR4, all right? And so my R total is just the 100 plus 100 plus 100 plus 100, which gives me a total of 400 ohms. And by Ohm's law, I know that V equals I, V total equals I times R total. So I is equal to the V total divided by R total. V total is just all the voltage sources added up because they're all in the same direction. So 4.5 volts, and R total is divided by 400 ohms. And I'm just going to pull out my calculator because my brain is not that good to do that quickly this late at night. And so I get 0.01125 amps or 11.25 milliamps. All right. And then if we decide to calculate VR1, I'm just going to put it in yellow so that it matches circuit colors. So VR1 is just equal to I times R1. And because actually all the resistors are the same, all of them are going to be 11.25 milliamps times 100 ohms, which gives me 1.125 volts. And that's also VR2, that's also VR3, and that's also VR4. And so when we add up VR1 plus VR2 plus VR3 plus VR4, we get 1.125 plus 1.125 plus 1.125 plus 1.125. Whoops, they don't look like 125s. 1.125, and that equals 4.5 volts, which is the same thing as our total voltage because of the 4 power supplies. So it just proves that it really doesn't matter where I put my resistors, where I put my voltage sources in a circuit, in a series circuit. It's very important to remember, in a series circuit where there's only one path, the total voltage is just going to be the sum of all the voltage sources, all the batteries. Your R total is just going to be the total of all the resistor values, and I is calculated by Ohm's law, V total divided by R total. And then you can go through each individual voltage and calculate each voltage drop using Ohm's law again. And there's our proof that, yes, this is true. Now, if you're still not getting this, in a couple of videos, I'm going to talk about something called Kirchhoff's voltage law. So it's just a proof. It's a way of proving that what I'm doing here, this whole calculation on top of Ohm's law, is correct. And really the position of where exactly I put each resistor and where I put every voltage source really doesn't matter. As long as we keep all our plus and minuses, all these potentials, higher potential, lower potential, higher potential, lower potential, straight, and we follow our convention for current, okay? And if we keep that all straight, it will always work out for series circuits, right? So again, if you have any questions, save them for class. You can send them to me by Mayo or email, and I'll be more than happy to answer it. But just the idea here, series voltage sources add up. Now, I want to just show one other one. And if I'm allowed to say it, it's no, I'm not going to say it the way I was going to say it. I'm just going to do another example. And I'm going to, on purpose, put the source in a completely different direction, all right? It's going to oppose the other source. So I'm going to say this one's 10 volts, and I'm going to say this one's 5 volts. And just to keep things simple, I'm going to keep all my resistors 100 ohms, all right? So I see that if I go clockwise, okay, my 10 volt source is like this, and let me assume that my current goes this way, all right? But when I hit the plus, this 5 volt source, I'm hitting the plus rather than the minus, all right? So it's opposite to the 10 volt source, because really, if sources are going to add up, I'm always going to, see the minus, go through it, gain the energy, and come out the plus on power supplies, on voltage sources, on batteries, okay? But here it's the opposite. So this is actually counteracting the voltage of this one. Now, why would you do this in real life? You wouldn't. This is just for, practice on paper, just to get the idea that sources add up, but you can also subtract a source if you put it the opposite way, all right? So it's really just to get that idea into your head that it's just a sum where you're adding plus or minuses depending on which direction you're going, okay? So if I assume my current is this way, and I know I'm right because this is the bigger source. So this is gonna be the stronger push on the electrons. So the current will flow in a clockwise direction, which means across this resistor, it's plus minus that way, plus minus that way, plus minus that way. And because they are all the same value, I'm just going to call it VR because they are going to be all equal, okay? We go back to our basic concepts of series circuits. R total is equal to 100 plus 100 plus 100 because we have 3 resistors that are all 100 ohms. So my R total is 300 ohms. Then we go to find I, and that's V total over R total. Okay, V total is the slightly trickier one, okay, because the 5-volt source is opposite to my 10-volt source. So it's not like the previous one where all the 1.5s added up. It's opposite. So it's actually going to take away 5 volts from the 10 volts. So my V total ends up 5 volts instead of 15 because of the direction of this source. If it was flipped the other way, then V total would be 15. So if it looked like this in the circuit, I'm going to erase that after, but just so that you see, okay, so if the minus was here and the plus was there and the current was flowing and it went in here, it would be adding because the electron is gaining power through the voltage source. That's the way I look at it. That's the way I try to explain it. So when an electron comes here, this is a lower power, but it gets energized by 10 volts. Then we lose whatever voltage here because the resistor takes away energy. We lose some more energy here. And if it was like this, it gained 5 volts, but because it's the opposite, it's plus minus, just like the resistors, we're actually losing that energy through that source. I know it's counterintuitive, but that is what's happening, okay? So I'm gonna erase this, and the video will be the only proof that there was actually something here before, right? So let's just do that calculation, 5 divided by 300, and we get 0.016, and the 6 is repeating. So I'm just going to put a line over it, okay? Amps, right? That little line over the 6 means the 6 repeats forever until the end of time, or it's 16.6 milliamps, all right? And if we want to find VR, well, it's just I times R, and I is 16.6 milliamps times 100. So we have, sorry, my brain is not functioning all that well. Okay, yeah. 1.66 with the 6 repeating volts. So each one of these voltage drops will be 1.66 volts repeating. So if we were to look at this, let's follow an electron now. We have a little electron here. It's not a good color because it's hard to see him. So I'm going to put it. So we have a little electron. It has energy, but let's say the net energy is 0. Okay. It goes through here and it gains 10 volts. So now the electron has 10 volts, right? Comes here and loses 1.66 volts. So if I'm at 10 and I lose 1.66 volts, the electron now here, it's a little hard to see. It's not a good color again. Maybe the orange. Orange is better. Orange is better. Let me go here. So electron, 10 volts. We lose the 1.66, so my electron now has 8.33 volts of energy. Then it passes the next resistor and loses 1.666 volts of energy again. And so now over here, the electron now has 6.66 with 6 repeating volts. Comes here, and because this is a plus, this is higher potential, I actually lose 5 volts. So that my electron now here has 1.666 volts repeating, not volts repeating, the 6 is repeating, volts. And then, lo and behold, look at that, VR has 1.66 volts also. So when I get back here, my net voltage is once again 0. So proof that as an electron passes through this circuit, there is conservation of energy. There's no extra gain or extra loss of energy. It's like whatever gets produced gets used up. And if I change a resistor value or a voltage value, everything changes based on Ohm's law and based on our concepts of series circuits. So I hope that made sense. I encourage you to do some practice problems, but I'll stop this video here and we will go to the next video to see the next